Next, we want to name some of the highlight some parts on this kind of graph, on these sinusoidal graphs, because they're always going to be doing this same thing. So first, I want to name a top, a middle, and a bottom, and you can probably guess where those are going to be. We're going to make this upside down. Down here at the bottom, that's going to be called the top. The top is going to be called the middle, and the middle is going to be called the bottom. Actually, that sounds insane. Let's do it the other way. Down here is going to be the bottom. Up here is going to be the top. And I'm going to call this line through the middle. Notice that in a sinusoidal graph, wherever we start, the sequence is always going to be the same. If we think about starting off at the bottom, this point is going to be at the bottom. This point will be at the middle going up, then we'll be at the top, then down to the middle going down, then the bottom, then the middle going up, then the top, then the middle going down, then the bottom. It's always that same sequence. So I want to refer to the two different middle points as the middle going up and then we get the top, and then we're at the middle going down. And then we're at the bottom, then we're at the middle going up. Then at the top, and then we hit the middle going down. So we only need a direction for the two different middle locations. The top is where things are turning around, and the bottom is where things are turning around. Bottom things are turning around, heading back up. Top is things turning around, heading back down. I want to name some distances. The distance from the middle to the top will always be the same as the distance from the middle to the bottom. And we're going to call that distance the amplitude. The amplitude is going to be the distance from the middle to the top or the middle to the bottom, because those are going to be the same distance. That's going to be the amplitude. We have periodic functions. These sinusoidal graphs are periodic graphs. And so we have to identify the period. The period is the distance between any 2 points with the same name, from bottom to bottom, the horizontal distance, from the bottom to the bottom, from the middle going up to the middle going up, from the top to the top, from the middle going down to the middle going down. A period will be the horizontal distance between any 2 points with the same name. Period is going to be a horizontal distance between any consecutive similarly named points. So the distance from the top to the top, that is one period. So from top to top, from middle going down to middle going down, from bottom to bottom, middle going up, middle going up. That'll be one period. So down here, if we have the bottom, there's one period, and that's where it ends. So from one bottom point to another bottom point, that's one period. Imagine the period as going around the circle one time. Or you're this way. Keep drawing it in my perspective. Draw it in your perspective. Think of the period as once around the circle. Your default period is going to be 360 degrees. Each of the named points represents a break in the quadrants. So each of the named points are a quarter period apart. So from the top down to the middle, that's 1/4 of a period. From the middle to the bottom, that's a quarter period. From the bottom to the middle going up, that's another quarter period. And from the middle going up to the back to the top, that's another quarter period. There's 4 of them. They correspond to the 4 quadrants. So for a cosine graph, here we have the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. Sine starts off at the middle going up. So from the middle going up to the top, that will be the first quadrant. From the top to the middle going down will be the second quadrant. From the middle going down to the bottom will be the third quadrant. And then from the bottom to the middle going back to the middle going up, that'll be the fourth quadrant. So each of these named points is a quarter of the period apart. So if the period is 12, it'll be 3 horizontally from the top to the middle going down, 3 from the middle going down to the bottom, and so on. Any questions? So you're on the named point. Top, the middle going down, the bottom, the middle going up. They're all a quarter period apart. From top to top is period. The horizontal distance between any 2 consecutive points with the same name is 1 period or 1 cycle. Any questions? Here's what we want to do. We know that the graph of, say, sine of theta has a period of 360 degrees and an amplitude of 1, because the top was at 1, the bottom was at -1, and it took 360 degrees to go all the way around the circle. So our default, so sine theta has an amplitude of 1 and period of 360 degrees. And so the question becomes, how can we change these values? Let's suppose that we're measuring some sinusoidal function and the distance from the middle to the top isn't 1, it's like 10. And what if instead of the period being from 360 degrees, the period is like 500 degrees? or only 10 degrees? How can we write a function? How do we modify our sine of theta function to fit that description? So which tool do I use? Calculator for a graph, even though it's bad at calculating? Let's look at our graph. Here's our graph of sine. Oops. Well, graph of glare. There we go. So we've got an amplitude of 1 and a period of 360. So if I trace it, when x is 0, or when theta is 0, we get 0. And when theta is 360, we're back to 0. When theta is 90 degrees, we're at 1. And when theta is at 270, we're down at -1. So if I want to change the amplitude, I want to take this graph and I want to stretch it vertically. Changes to the amplitude will stretch the graph vertically. A change to the amplitude will stretch the graph vertically. A change to the period will stretch the graph horizontally. So if I want to change the amplitude, I'm going to stretch the graph vertically, or stretch the graph vertically in the other direction, squish it vertically. Same thing with the period. I can either stretch the graph vertically to change, or I want to stretch the graph vertically to change the period, or squish the graph vertically to change the period. So now we just have to experiment. I'm going to say, what happens if I take the sine x and multiply it by 2? We can see that when I take the sine x and multiply it by 2, I have stretched the graph vertically. Note that the amplitude has increased. If I trace and look at what's going on at 90, oops. On the graph of sine of x, we're at 1, and on the graph of 2 sine x, we're at 2. So we multiply by 2, we stretch the graph vertically by a factor of 2. So it's not going to be surprising if I go down here and multiply by 3. That's just going to stretch the graph even more. Note that I didn't change what the period was at all. It still goes through one cycle in 360 degrees. All we've done is change the amplitude. Questions? So here we are multiplying by 2 and 3. If I multiply by something less than 1, what will you expect to happen? So multiply the sine x by 0.5. What do you expect would happen? To squish it, but the period should stay the same. All those x-intercepts should be the same. And that's exactly what happens. We just squish our amplitude. Multiplying by more than 1, stretched. Multiplying by less than 1, squished. That makes sense because multiplying by 1 doesn't do anything. Multiplying by more than 1 makes stuff bigger. Multiplying by less than 1 makes stuff smaller. 1 is called the multiplicative identity. It's the middle of multiplication. 0 is the additive identity. It's the middle of addition. So positive and negative for addition. Let's see what happens if I multiply by negative 1. What do you think is going to happen if I multiply by negative 1? Flip the whole graph. That makes perfect sense because here we are at 1. If we multiply by less than 1, it gets smaller. If I multiply by 0, it goes away. So if I multiply by less than 1, it should appear on the other side and just keep on going. So let's find out. And there it is. There's our graph of negative sine x. It just flipped it over. It's getting a little bit messy. Oh, and it's on sequential. Any questions? How's everybody okay? Everybody looks so fascinated. You all look like this. Because you're mostly falling asleep. That's okay. See, after I'm done like with the teaching career, I'm going to open up an insomnia clinic. And the great thing is, I'm going to do exactly the same thing, only with comfy chairs. Instead of chairs that are like always sliding and trying to spin you somewhere, it's going to be like a bunch of like comfy lazy boys. And instead of this harsh fluorescent light, it's going to be like nice soft light. And then when I come in, instead of turning the lights on and making it all bright and harsh and annoying, it's going to be warm, soft light. I'm going to tone it down a little bit and be like nice, soft, warm light. And instead of using my normal voice, I'm going to hire someone who has a more soothing voice. And they'll come in here. Today, we're going to talk about the graphs of sine and cosine. And it'll be, come to Leach's Insomnia Clinic. We'll cure you in 1 visit. Oh, how does it work? I use the power of math. You mean you study patterns of sleep and applied statistics? Oh, no, I just talk about it. I just find out where a person's highest level of math was, and I talk about that. Any questions? Here's the cool, here's an interesting one. Let's get rid of these. So we totally understand how amplitude is going to work. Whatever we multiply the sine by, we put that multiplication on the outside, we're going to stretch it or switch it or flip it. Let's see what happens if we start multiplying inside. So instead of 2 sine x, I'm going to do sine of 2x. Oh, I forgot to switch to simultaneous. I gotta wait for both of them to fall. So now when we look at this graph, it looks like it's moving through faster. Notice if we trace this red graph, when x is 90, we're back at 0. And when x is 45, we're at the top. And when x is at 180, we've gone all the way through. Notice that when x is 180, we're going twice as fast. And so that's how we can interpret that 2 in front of the 2x. It's getting us from 0 to 360. It's sending us around the circle twice as fast. So when x is 180, this function has already gone around the circle to 360. So that's why multiplying by 2 has squished the graph in, has made compression. Because the x, instead of the x-axis just being x, it's going twice as fast. This is kind of the opposite of what we saw in the amplitude. When the multiplication took place outside of the sign, it stretched things out. But when the multiplication by 2 happened before sign, it squished things in. That seems like a messy thing to remember, but moving forward, the thing that you can take solace in is that it always works that way. Multiplication after the function is going to stretch vertically. Multiplication before the function will squish horizontally. Now, if we're going through the circle of 3x, if we're looking at the sign of 3x, we've gone around the circle when x hits 120, because 3 times 120 is 360. So sine of 3x is going around the circle 3 times, when sine of x goes around once. And if we want to slow things down, because we're opening up an insomnia clinic, if I divide by 2, that's going to stretch things out. Questions? Of course not, because we're familiar with these concepts, because we have radios in our car. We have frequency modulation, where this is how we're changing the signal, and we have amplitude modulation, where this is how we're changing the wave. Then, of course, we have XM, because it came out of time when everything was extreme. When did XM come out? Anyway, it's extreme. So if you're listening to XM radio, if this is like the early 2000s, then you'd have to drink Mountain Dew. And you couldn't just drink it like a normal human. In the early 2000s, if you're drinking Mountain Dew, you had to drink it extreme style. And like open up the bottle and just pour it into your face from up here. If I start describing stuff that happened in the 90s and say, that sounds awful, I'm glad I wasn't there, you probably, that's the correct answer. That sounds awful, I'm glad I wasn't there. I don't know if it still happens, but you know, it's like people are like, well, I'm gonna wear 2 shirts, a long sleeve shirt and a short sleeve shirt. I'm gonna put the short sleeve shirt on top so my sleeves stick out. And there's still something written on my long sleeve shirt, but I'm gonna cover it up with a short sleeve shirt. Questions? Old people still made fun of the way young people dress. That is always going to happen. Never give a shit about what old people have to say about what you're wearing. If old people are like, oh, pull up your pants. Hey, Grandpa, I found some pictures of when you were a kid. And Grandpa had his pants, they were up to here. He was wearing his fucking pants way up here. And he had this little tiny tie. So, nah, I ain't hearing it. It really drives me crazy when people my age are making fun of the way people dress. So I'm like, oh, motherfucker, I saw you dressing up in the 80s. Oh, here we go. Let's peg our pants. Yeah, no. Or the short shorts, yeah. In the early 80s, kind of tailing on the 70s. Let's make some shorts and really emphasize the shorts. And they're like short shorts. Anybody ever watch a basketball game from the 70s? What are we talking about? Don't let old people make fun of your taste, because their taste in music is just as shitty. I mean, seriously. Also, don't make fun of people your own age for their taste in music, because your taste in music is just as shitty. Your taste in music is stupid. My taste in music is stupid. Your taste in movies is stupid. My taste in movies is stupid. You know what I mean? Don't make fun of people for stuff that they like. That's like dumb. So anyway. Or at least if you do, make sure that people don't think that you're taking yourself seriously. Because if someone's like making fun of the way you dress, and you're like, ah, yeah, that's funny. Oh, wait, you're being serious? Oh, how pathetic. Grandpa. The funny thing is when old people are making fun of young people, like they invented it. Old people have been making fun of young people since there have been old people and young people. Like I'm sure that at some point Socrates was walking around in his friggin' toga. They're like, can you believe kids these days? They're wearing their toga way down here. What's going on? And young people in Socrates' days like, oh, shut up, old man. Go think about some more stuff. All right, what are we talking about? Oh, yes. So the thing that these two operations have in common, changing amplitude and changing period, is that we're stretching or squishing, and both of those are covered with multiplication. The vertical changes, we did multiplication after the function because it was 2 times the sine of theta. Theta hits the sine first, then we multiply by 2. That made a vertical change. The horizontal change came about because we did the multiplication before the trig function. We multiplied theta by 2, then we applied the trig function. Multiplication before will produce a horizontal stretch. Stretch because multiplication, horizontal because before. Multiplication after will produce a vertical stretch. Vertical because after, stretch because multiplication. That's the way we want to associate these things. We've got one more operation to apply. That's going to be addition. Addition is going to shift things. Addition is going to be about shifting. Vertical shifts will be addition after the function. Horizontal shifts will be addition before the function. Any questions? Yes. And addition after the function will move it vertically. And remember how the multiplication by 2 stretched things vertically, but squished things horizontally. If we put a +2 after, that's going to move it up 2. But if we put a +2 before, it's going to go left 2. All right. So think about those changes, and we'll summarize this. This is more useful than just sinusoidal functions. This is functions in general. We're talking about a bigger topic than just sinusoidal functions. We're just using sinusoidal functions to get there. That's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Have a good weekend, and thanks for playing.